Yeah. Well, first off, there's only 3 people in that class, and they're all very quiet.
It's such a depressing.
There's only 3 people?
Yes, and Monday, Thursday. Okay.
And then you make a joke and everything's just completely silent.
I know. It hurts my feelings too. So don't. You know, I love the interaction. I need this. So I'm thankful that there's at least a few people in here, but it's so much better when it's full.
That's so good. I'm gonna take
Only 3 more weeks.
Well, we'll see. We'll see. All right. So at the end of the video yesterday, we started talking about polar bonds and polar molecules. The Earth has poles. It's got a North Pole and a South Pole. What does that mean?
That's where Santa Claus is from.
Okay. Santa Claus is at the North Pole. Okay. Well, why do we call it a North Pole and a South Pole?
That's magnetic.
It's a magnetic north. It's a positive and a negative. Now I don't know which one is classified as the north. I don't know if that's positive or if that's negative.
The one that's up.
The one that's up is
The one
positive.
that's at the top.
Okay, it's positive.
Oh,
Okay.
I thought you meant like which one's the North Pole.
Oh my god.
I don't know which one's positive, which one's
Sure he
negative.
doesn't.
Okay, yeah, I do know that the North Pole is the one at the top, and the South Pole is the one at the bottom. I do know where Santa Claus lives.
I was so
Okay.
confused. I was like, what?
All right, so when we're talking about a polar bond, that's one that's going to have a positive and a negative end. It's going to be the result of an uneven sharing of electrons. We're talking about covalent bonding, which is supposed to be the sharing of electrons, but it's not always shared evenly. If you get out the periodic table that I gave to you, does anybody have one handy? Yes, this one right here. Okay, and you look at the back of this periodic table up at the top, you can see where it says the difference in electronegativity in black and the percent ionic character in red. And so when you're looking down here, when the difference in electronegativity is very small, then the percent ionic character, in other words, the amount of positive and negative, the amount of uneven sharing of the electrons is very limited. So we say that that's a non-polar bond. The electrons are going to be shared equally in the whole molecule. There's not going to be any uneven distribution. Then there's kind of the gray area between 0.4 and 1.7, where it's going to be not strong enough. One's not strong enough to completely take the electron away, but it's definitely not an even sharing. The electron hangs out more around one than it does the other. And what happens at 1.7?
It becomes ionic.
I know, but what's the percent?
51.
51%. Now it's more ionic than it is covalent, so we call it an ionic bond. Now the reality is it's still an uneven sharing, but we're saying it's so uneven that it's more of an ionic, more of a transfer than a sharing. It's not until you put these compounds, the ionic compounds, into water do the ions actually completely separate from one another. Okay? So it's a sliding scale as far as how the electrons are shared between the two atoms. Now, it's real important that you understand that when I'm looking at HCl, chlorine, I'm going to use X's just to show chlorine's electrons. The covalent bond is the sharing of this pair of electrons. It's this electron, hydrogen's electron being drawn to the chlorine as well as to the hydrogen. This one's being drawn here and here. So they're being pulled both ways by the two nuclei. The electronegativity is a measure of how strong of a pull do they have for that shared pair of electrons. It's a tug of war. They're going this way and hydrogen's trying to pull it this way. It's a scale from 0 to 4, with 4 being strong, 0 being weak. Okay? That's what electronegativity is. It's a measure of how strong of attraction do these atoms have for a shared pair. In this particular case, chlorine, and you look on the back, you get this on the back side of your periodic table, they give you the value. You don't have to ever memorize this. We're going to talk about trends, but 3.16 is chlorine, hydrogen's is 2.20. So on a scale of 0 to 4, that's a fairly significant difference, which means chlorine has a much stronger attraction for this shared pair of electrons than hydrogen does. But it's not quite strong enough to completely take it away. It's not going to be a transfer of electron. We're not going to make an ionic. It's just going to be an uneven sharing, which means that when I'm looking at the electron cloud here, the electrons are going to be a lot more dense over in this area around the chlorine, which is going to give the chlorine a partial negative and a partial positive over here on the hydrogen. And that's a Greek letter delta. It's the same for math when you do integrals, if you ever get into calculus. Okay? Positive and negatives. But it's a partial positive, partial negative. It's not a complete transfer, it's just an uneven sharing. So we use this to differentiate between an ion and a polar. Okay? It's an uneven sharing. Now, what's the trend in electronegativity on the periodic table? We had to learn that in chapter 5.
Left to right, it gets higher.
Left to right, it increases.
Top to bottom, it decreases.
Top to bottom, it decreases. So fluorine is the highest, francium is the lowest. Okay? Francium is the highest, fluorine is the highest, francium is the lowest. And so, as a whole, the alkali metals have the lowest electronegativities. The halogens as a family have the highest electronegativities. So when you put an alkali metal and a halogen together, you have a big difference in electronegativity. We have an ionic bond. They're so different in electronegativities, one can just take the electron from the other one. But when you start combining nonmetal with nonmetal, now the electronegativities are much closer. However, when you're looking here, fluorine, oxygen, nitrogen, and chlorine, fluorine, oxygen, nitrogen, and chlorine, these are your big four. Fluorine's number 1 at 3.98. Oxygen's number 2 at 3.44. Nitrogen's number 3 at 3.16. Chlorine is 3.04. Okay? These are the only ones that are above 3. If one of these are involved in the bond, normally, pretty much you can be guaranteed the difference in electronegativity is going to be greater than 0.4, and it's going to be a polar bond. So rather than having to go and look up the electronegativities every time, subtracting and trying to see where it fits, we can just pretty much say a metal and a nonmetal is going to be a big difference. We're going to call that ionic. Two nonmetals, if you got a fluorine, an oxygen, a nitrogen, or a chlorine, then it's going to probably be a polar bond. If you have two nonmetals but they don't have any of those, it's probably going to be a much smaller difference. It's probably going to be a nonpolar bond. If it is polar, it's going to barely be polar. Okay? So we can determine the type of bond just by kind of position and what atoms are bonding. But for the molecule, there's two criteria. Not only does the molecule, for a molecule to be polar, overall, we can have polar bonds, but for the molecule to be polar overall, we have to have at least a polar bond, at least one, but it must be asymmetrically shaped. Yes, sir.
So you said the phone call thing, that's polar.
Those are going to be polar. If they contain this, they're going to have polar bonds. Okay? Now, if you're looking on page, probably what, 4 or 5, 6, where it starts at B, polar molecules.
6.
Okay, it's page 6. Okay? I'm giving these two criteria. So now we're going to look at, for all molecules, what I'm trying to be the 2A. What goes in that blank is AX4 molecules. Anything that fits into this AX4 pattern. Okay? If it's going to be are symmetrical, if all 4 bonding atoms are the same. Okay? If not, it's going to be asymmetrical. For example, okay, they have the CCl4, carbon tetrachloride, versus, what's the other one I gave? CHCl3. okay? This one's gonna be symmetrical, this one's gonna be asymmetrical. And by the way, when you're spelling the word asymmetrical, again, only one S in asymmetrical. When you're spelling it, you don't want to say A-S-S-Y-M, because then you're just really kind of being an ass, okay? Don't be an ass, spell asymmetrical correctly with only one S. Okay, so if you're spelling it and you see the word ass, adjust. Okay? I said that on video. And so, all right, so when we're looking at this, the best thing to do is look at these in models. So we have chlorine. Oh shoot, I took off the green one. Yeah. So I'm looking here at CCl4, okay? Now, we do have chlorine, so I have 4 polar bonds, okay? Which means that the chlorine is the more electronegative element. It's pulling the electrons this way. But this chlorine is trying to pull the electrons this way. This chlorine is trying to pull them this way. This chlorine is trying to pull them that way. So all 4 pulls are totally symmetrical. They're pulling in opposite directions. So the electrons end up not going anywhere. Because it's symmetrical, so the pulls cancel out. So as a result, this is a non-polar molecule. It's going to have an even distribution of electrons. There's not going to be any positive or negative ends. Okay? So if the molecule is symmetrical, it's automatically non-polar. Maybe write that in the margin. If the molecule is symmetrical, it's automatically non-polar. Now, so now if I just replace one of the chlorines with a hydrogen, now the chlorines are pulling this way, and this way, but the hydrogen's not electronegative at all. Actually, it's less electronegative, so the electrons are still being pulled down towards the carbon some. So everything has got a downward or upward, however you want to look at it. It's all going towards the chlorines. So now there's no longer symmetrical, so now the pulls don't cancel each other out, and so the electrons get pulled more toward one side than they are the other. We get a polar molecule. Okay? So we look at the symmetry of the molecule. So then the next one, again, AX3 molecules are symmetrical if all 3 atoms are the same. But if 2 are the same and one's different, then it doesn't matter. And don't worry, it doesn't matter whether it's a double bond or a single bond, that doesn't matter. But if all the X's, all the bonds are the same, it's symmetrical. If they're not, it's asymmetrical. And AX2 molecules, same thing. They're going to be linear. If everything's the same, then they're going to be symmetrical. If they're not, it's not. So if we look at HCN, that's going to be asymmetrical. And we have a nitrogen in it, so that means I have a polar bond. It's asymmetrical, that means it's a polar molecule. But CO2, I still have 2 polar bonds because of the oxygens, but they're symmetrical, so they cancel each other out.
So like on the top one, if that hydrogen was a nitrogen, it would be
Yeah,
symmetrical.
it would be symmetrical. Okay. Now it can't form that, but if it were, if they're the same on both sides, yes. Now, what you can't do though is you can't trust your Lewis dot structure, because if we have one that looks like this, that looks very symmetrical. But you're looking at something in 2 dimensions that exists in 3 dimensions. The reality is it looks like this. And so the chlorines are being pulled here, the chlorines are pulling the electrons there. There's nothing over here to balance that out. You're kind of looking at it like this with no depth perception. Okay? So you can't trust your Lewis dot structure. You got to trust the rules. Okay? Now, generally speaking, if the central atom has a lone pair of electrons on it, the shape will be asymmetrical. It's not the lone pair that's making it polar or whatever, but most asymmetrical shapes have a lone pair on the central atom. So you can pretty much use that as a guide. You look for phone call to determine whether or not it's a polar molecule, polar bonds, and then you can just kind of look, do I have any lone pair? If I have lone pair, it's probably asymmetrical. But if I don't have any lone pair, then I have to make sure all my X's are the same for it to be symmetrical. If they're not, it's asymmetrical. Now there are two exceptions to molecules that have lone pair on the central atom, but they're still symmetrical. AX4E2. AX4E2, if the X's are all the same, it's a symmetrical molecule even though there are two lone pair on it. The other one is AX2E3. It's going to be linear. That's going to be symmetrical as long as the two bonding atoms are the same. So those are two exceptions to the rule of lone pair. So you can't really say it's asymmetrical because it has lone pair. Well, no, these have lone pair and they're asymmetrical. Generally speaking though, if the central atom has a lone pair, it's an asymmetrical shape. The lone pair is not making it polar, but it's an easy way to determine that the shape of the molecule is asymmetrical or not. Okay? So what makes a molecule polar is you have polar bonds and you have an asymmetrical shape. We just have to figure out a way to get the asymmetrical shape. So, let's look at that same worksheet we've already done a bazillion reactions on. Okay, so we've drawn the Lewis dot structure. We've got the AX formula, the type of hybridization, and whether or not we know the shape of the molecule. Now we're going to do the last part of the assignment, which is going to be polar or nonpolar. So if we look at number 1, that's SO3, correct? Okay, so we already have the Lewis dot structure drawn. Okay, looks like this. Okay, so I know this shape is trigonal planar. The type of hybridization is what?
SP2.
SP2. Okay, because it's AX3 is my shape. Is my general formula, not the shape, it's my general formula. Okay? 2 plus 1 adds up to 3. Now, I need to say, is this going to be a symmetrical or an asymmetrical molecule? It's symmetrical, right? Because it's an AX3, all the bonding atoms are the same, there are no lone pair on the central atom, so it's a symmetrical molecule. So what does that automatically mean about its polarity?
It's nonpolar.
It's nonpolar. Symmetrical is automatically nonpolar. Okay? Now, feel free. This is kind of complicated, so if there's anything that's fuzzy, this is the time to work it out. Okay? What's the next one? What's number 2?
HNO2.
HNO2. So then we have the nitrogen, oxygen. Remember the hydrogen attaches to the oxygen. We have a double bond oxygen here and a lone pair there. Now in this case, well, first off, we have oxygens present, right? That tells me I have polar bonds. Secondly, is this going to be a symmetrical or an asymmetrical molecule? It's asymmetrical. You got lone pair here and you got lone pair there. So it's asymmetrical. Now we say the shape, it's bent around this one, bent around that one, but it's sp2 hybridization, sp3 hybridization. You already have that written down. Okay? But it's going to be an asymmetrical molecule. It's got polar bonds, so what does that mean in terms of the polarity? It's a polar molecule. More so here. Here are the electronegativities. I'm just going to point this out. 3.16, 3.04, pardon me, no. Try this again. 3.16, 3.44, and then 2.20. So this difference right here between the nitrogen and the oxygen is two big bad boys battling it out for the electrons. So it's pretty close, 0.28. But this bond right here, oxygen and hydrogen, oxygen's hogging the electrons from the hydrogen. Same thing on this one, 3.44 here, so there's not a big difference. So the polarity part is really right there. To where the electrons are drawn to the oxygen, the hydrogen gets positive, the oxygen gets more negative. Okay? Now you don't have to really know that part of it, but I'm just kind of showing you how that works. What's number 3?
SiO2.
SiO2. Do we have polar bonds? How do I know just like that? It's got oxygen. So I got 2 polar bonds. But this is AX2. Are both bonding atoms the same? So what does that mean about symmetry?
It's symmetrical.
It's symmetrical. So what does that mean about polarity? It's nonpolar. Okay? Do you understand how to do that? So let's just use, maybe even the rest of the period, to see what you can do on those, and then we'll come back and go over them. Yes, sir.